Is your calculator giving you domain errors? Let's talk. What is up, mathletes? So today we're going to look at domain. Big topic, right? Because I know when I left algebra, jumped into calculus, I still didn't really have a good understanding of domains back in the day. And till this day, when I teach calculus, people I could tell really don't have an understanding either. So here, let's bring it down a notch. Let's really get into the nitty gritty and let's understand what the heck a domain is. All right. So first, let's go ahead and read this, and then we'll break it down further. We'll translate it into English for you. All right. So the domain, we could write it as the list of all possible x values that can exist in the function. And I see all the question marks, right? Just populating. And so the way I want you to think about it are, let's look at this first linear function here. What values of x can I plug in there that when I plug it into my calculator, it's not going to give me an error. It's going to give me some answer. I don't care if it's a fraction, decimal, whatever, but I get an answer. It's not going to give me an error. So what I'm looking for is all the x values that I'm allowed to plug in. That's what we think about when we think about the domain. And when we're talking about linear functions, right, which is just a line, I graphed it for you. I'm looking at this line and I'm looking at what are the possible x values. So if you give me an x value such as 1, what's going to be that height, right? That's what we're looking at. And so you give me any x value and I'll be able to tell you the height of that graph, the output, and that's what we're looking at here. So when we look at linear functions that look just like this one, what you're going to note is that the domain is going to be all real numbers. And what I'm going to do is I'm going to write it in interval notation for you, right? So here, I don't have any restrictions. You give me any number and I'll be able to plug it in there without a problem, all right? So hold with me because be patient, because at the end, right, we're going to look at some functions here that will have some domain issues, and we'll talk about that. For the second function, what I'm looking at here is I'm looking at quadratics. So I'm trying to figure out what number am I not allowed to plug in here. That would give me a problem. So for example, if I plugged in 0, does 0 give me a problem? Well, this will turn into 0, this will turn into 0, and I would get an answer of 7. So 0 doesn't give me any type of problem. In fact, you give me any x value for this function, and I'll be able to tell you what the height is, the y value. And what I did here, and I should have some arrows here because this function is going to go on forever, is you give me any x value and I'll be able to tell you a height. So the domain for this function, this quadratic, is also all real numbers. We don't have any domain issues. So we go from negative infinity to positive infinity. Here's another way of looking at this to kind of help you understand. When I'm looking at all possible x values, I tell my students, how far left does the graph go and how far to the right? And are there any holes in my graph? Are there any pieces of my graph missing? And so let's go to that top one, the linear function. So see this line, how far to the left is it going? Well, there's an arrow, so it's going all the way. It's going to go to the left. And so it's never stopping. So it goes towards negative infinity. And how far to the right is my graph going? Well, it's going to infinity and beyond. And so we write it goes all the way to infinity. And we use these open parentheses here, right, to make sure to tell the audience we never actually get there, right? And so the same thing here with this quadratic. So these, whenever you see a quadratic function or a linear, the domain is going to be all real numbers when they look like this. There's going to be some linear functions, right, we'll talk about later, very few forms of linear functions that are going to cause some problems, but they're very special cases. We'll look at that later. Next, this polynomial here, right? So what I did is I drew a graph on Desmos. You guys should check out Desmos if you never used it, desmos.com. And I used it to graph this right here. And what I see is how far to the left is my graph going? Well, to the left, it's going to go on forever. So it's going to go all the way to negative infinity. And my graph here is going to go all the way to the right, and it's going to continue going to the right, to the right, to the right, and it's going high, but we don't care about the height. All we care about for the domain is how far to the right. And you can see it's going to go on forever. So it goes off to positive infinity. So when you see functions in these three forms right here, you know the domain is all real numbers. All right, now let's get into the more interesting questions for domains. For example, what happens when we have a rational function, right? When we have a rational function, that's a special way of saying we really have a fraction, right, with some variables in it. So what we look at here is, what numbers, if any, can I not plug in here? So we think, because I have a division, remember you can never divide by what number? That's right. If you heard that creepy person behind you, they said you can't divide by 0. So what we look at is, what number do we plug in here to make this denominator equal to 0? So a lot of people at first glance here, they could say, oh, x cannot equal -5. Because if I were to plug in -5 for x, right, I'll get -5 plus 5, and that would make this 0. So if you type that into those fancy calculators, they'll probably say domain error. If you plug it into one of those calculators from the 99-cent store, it'll probably start to smoke, and then you have to go buy yourself another one. All right, so what happens when these problems get a little bit more challenging? Well, take a look and take down these notes. Whenever you have a rational function like that, what you're going to do is you're going to set that denominator, and you're going to tell yourself that that denominator could never equal 0, not even on Sunday. All right, so we set it equal to 0 here, even though it's not equal to 0, and we isolate x. So let's go ahead and let's subtract 5 from both sides, and you get x equals -5. Excuse me, x cannot equal -5. So this is what the process looks like. So again, whatever is in our denominator, what we're going to do is we're going to set it not equal to 0. So x could be any number in the world, any real number except -5. So let's draw that out. All right, so we could see what that looks like. So we said the only problem child here is -5. So right there at -5, I have an open circle to indicate it cannot equal -5. So what we're going to do is we're going to shade everything to the left of that, right? Because x could be any number smaller than -5, and x could be any number greater than -5. So because we have that gap in the middle, the way we write this using interval notation, and if you want an interval notation video, make sure you comment down below and let me know. And very important here in this next step, don't forget to subscribe and like and help us out. All right, help us promote this channel. All right, so let's see. How far to the left is this graph going? Well, this graph is going all the way to negative infinity. So that's where we start. So we start at negative infinity. And we go from negative infinity, right? And then we keep going in the positive direction until we hit, boom, this -5. So we hit -5. And what we do is we ask ourselves, can x equal -5? It cannot. So what we have here is we have an open parenthesis. And whenever we have a gap here, right, on our number line, what we do is we use the union sign, a U. Not me, but you.
You!
Yes?
Not you, him! What's your name?
Me.
Yes, you!
I am me. He's me. And I'm you.
All right, and we ask ourselves, all right, we start back up at -5, and then we go all the way, look at our graph, it goes all the way to positive infinity. So we go all the way to positive infinity. All right, and so this is our domain right here. This is our domain. And again, you use this idea, you use this logic with any type of problem that you get, especially for rational functions, right? Later on, right, you could get a function that looks like this. Let's put 3x over, I don't know, x squared minus 9. And we use the same type of thinking. So here, we would make sure that that denominator cannot equal 0. And I'm sure if you're already talking about rational functions, you've learned how to factor. So we would factor this. Notice you have perfect squares and you have a subtraction. So you would use the difference of squares formula. Remember, a squared minus b squared. So let me write that down just in case you forgot. A squared minus b squared. And the way that factors is a plus b times a minus b. And again, if you need more help on factoring, I have a video link right down below to help you out with factoring difference of squares, just like this one. All right, so factoring this, let's go ahead and factor this, mother sucker. And we get x plus 3 and x minus 3. And all I did, a little shortcut, is I took the square root of this, boom, put it there and there, because x times x gives me x squared. Took the square root of 9, 3 and 3. We slap a plus, we slap a minus, and we're done, right? So, but make sure we have to be consistent, what we said earlier. We don't want it equal to 0. So what we say is that both of these factors here, both of them, better not be equal to 0. So we solve each one, so we subtract 3 from this one, and we get negative 3. X cannot equal negative 3. And we add 3 to this one, and we say that x cannot equal positive 3, right? So when we're looking at our number line for this problem right here, right, we have two numbers that x cannot equal. We say that x cannot equal negative 3, it's somewhere over here, put an open circle here, and x cannot equal positive 3, we'll say that's over here. So x can be any number in the world. Right, so I'll make that line go that way. Anything between negative 3 and 3, and anything greater than 3. So x could be any number in the world except negative 3 and positive 3. So the way we write that using interval notation is you go from left to right. So where does this graph start? It starts over here at negative infinity. So we go from negative infinity until we get to the first problem child, which is negative 3. Remember what we said earlier, we do the U for union, right? And then we start back up at negative 3, and we're not including it. And then we go from negative 3, let's look here, it goes from negative 3 until it gets to, boom, 3. So we got 3 right here, put the union sign, and then we start from 3 again, and it goes all the way to positive infinity. But the process is exactly the same. So there is our final answer. And that's what's great about math, right? We're consistent with our process. Some little details might change in terms of you might need more skills. Just like here, we actually had a factor. Over here, this was a nicer problem, right? Over here, it required a little bit more work. But the idea is still the same. You set the denominator equal or not equal to 0, right? So the idea stays consistent. So this is how you're going to handle rational functions. And let's talk about our last idea for the day, because I see you. You're getting tired. Hang on.
Housekeeping?
No, thank you. Sleeping.
Let's close up shop here. Let's talk about square root functions. And just think about it. What numbers can you not take the square root of? All right, we cannot take the square root of. Remember, when you take the square root of a number, whatever's in here cannot be negative, right? It cannot be negative. It has to be 0, right? Because you could take the square root of 0, but you can't take the square root of negative, because then you start getting into imaginary numbers, right? We don't want that. It's kind of like a lot of your friends, they're imaginary. We're not going to talk about that.
There's something going on in this house, Professor. I'm not crazy! Ah!
All right, so what we do here is we take the argument, which is the inside of that square root, and you have to make sure that it's positive or equal to 0. And those are the numbers that we're looking for, the non-negative numbers. So let's go ahead and solve this, and we get minus 5 on both sides of this inequality. And so you get x has to be greater than or equal to negative 5. So let's go ahead and draw that. X has to be greater than or equal to. So this time we'll have a solid circle, right? Because this time we are including -5. And so it's all the numbers that are greater than -5. So let's see where we start. Well, we just said we're starting at -5 for our domain. Because if I plug in -5, I get -5 plus 5, which is 0. That's okay. And because we're including it, we're going to use a bracket here. And so write that down. That means that it's part of the solution. That -5 is okay. It's part of the solution. And we go all the way to positive infinity. So again, when you're looking at square roots, make sure that you take the square root of whatever's in the inside, and we call that the argument. All right. So hopefully this video was helpful, folks. We talked about a lot, but let me know if you wanted me to do any more specific examples. We could dive in there and dissect those. All right. Don't forget to like, subscribe, and we'll see you mathletes next time. Peace.